Today we're going to continue our discussion of vector spaces and subspaces. A while back we talked about a linear combination. Today we're going to visit linear combinations, and we're going to talk about the set of all possible linear combinations that can be formed from the vectors within a set. That set of all possible linear combinations has a special name. It's called the span. And then we're going to start talking about some of the properties of the span of a particular set of vectors. A vector V in a vector space, capital V, is called a linear combination of the vectors u1, u2, uk in V if scalars c1, c2 up to ck can be found such that V is equal to c1u1 plus c2u2 plus up to and including ck uk. Now remember that bold print indicates vectors and that regular print indicates scalars. So u1, u2, and uk are vectors. c1, c2, ck are scalars. So vector V is a linear combination of vectors u1 through uk and scalars c1 through ck. The concept of linear combination is used quite often, so you really need to make sure you understand what it means. I'm going to give you a couple examples to help make it clear. Example, write 1, 17, negative 17 as a linear combination of u1 equals to 1, 2, negative 2, and u2 equals to 2, negative 1, 1. Well, if I write it as a linear combination, that means I've got to find C1 and C2 such that 1, 17, negative 17 is equal to C1 U1, which is 1, 2, negative 2, plus C2 U2, which is 2, negative 1, 1. Or I get 1, 17, negative 17 is equal to C1 plus 2, C1, 2, C1, negative 2, C1, plus 2, C2, negative C2, C2. Just multiplying through by the C's. Now using vector addition, I get C1 plus 2C2, 2C1 minus C2, a negative 2C1 plus C2. Now I can equate the coefficients to get that 1 is equal to C1 plus 2C2, that 17 is equal to 2C1 minus C2, and that negative 17 is equal to a negative 2C1 plus C2. Or I can write the system in matrix form as the coefficients for the first one would be 1, 2, 0, the constant is 1. For the second equation, coefficients would be 2, negative 1. Actually, I don't have a third column there, so it would be 2, negative 1. The constant is 17. And then it would be a negative 2, 1. Constant is negative 17. So I need to reduce the matrix, write it in row echelon form, so I can solve the system. I can simply add rows, or add row 2 to row 3. So I'd have 1, 2, 1. 2 plus negative 2 is, I'll go ahead and write down the 2, negative 1, 17. Then 2 plus negative 2 is 0. Negative 1 plus 1 is 0. 17 plus negative 17 is 0. So my third equation is 0 equals 0. Now I need to get rid of the 2, so what I'm going to do is multiply row 1 by negative 2, add to row 2. So it'll be 1, 2, 1. Negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times 2 is negative 4, plus a negative 1 is negative 5. Negative 2 times 1 is negative 2, plus 17 is 15. And we still have 0, 0, 0. Now I'm going to multiply by negative 1/5 on row 2. And that would be 1, 2, 1, 0, 1, negative 3, 0, 0, 0. Multiplying by negative 1/5, same as dividing by negative 5. So negative 5 divided by negative 5 is 1. 15 divided by negative 5 is negative 3. So I can just read and see now that C2 is negative 3. I can see that C1 plus 2C2 is 1. So C1 is 1 minus 2C2. So C1 is 1 minus 2 times a negative 3, which is 7. So I have found, so we have found the desired constants. C1 is 7, C2 is negative 3. So we can go back to where I wrote it. 1, 17, negative 7 is equal to C1 plus C2. If I go back and replace C1 and C2 by what I solved for, we'll see that it is a linear combination. So we got that C1 was 7, and that C2 is negative 3. Well, this would be then the point 7, 14, negative 14. This would be the point negative 6, 3, negative 3. Well, if we add the 7 and the negative 6, I would get 1. Add the 14 and the positive 3, I get 17. Add the negative 14 and negative 3, I get negative 17. So now we have the linear combination. Determine whether 0, 2, negative 1, 0 can be written as a linear combination of 6, negative 7, 8, 6, 4, 6, negative 4, 1. Well, if it can, that means I can find C1 and C2 such that 0, 2, negative 1, 0 will equal to C1 times 6, negative 7, 8, 6 plus C2 times 4, 6, negative 4, 1. Because if it can be written as linear combination of these two vectors, I can find C1 and C2 so that C1 times the first vector plus C2 times the second vector is the given vector. Where I get that 0, 2, negative 1, 0 is equal to 6 C1, negative 7 C1, 8 C1, 6 C1 plus 4 C2, 6 C2, negative 4 C2, C2. Well, I use the scalar multiplication. Now applying vector addition, I get 0, 2, negative 1, 0 is equal to 6 C1 plus 4 C2, a negative 7 C1 plus 6 C2, 8 C1 minus 4 C2, 6 C1 plus C2. Equating the components, I get that 6 C1 plus 4 C2 is equal to 0. A negative 7 C1 plus 6 C2 is equal to 2. 8 C1 minus 4 C2 is equal to a negative 1. 6 C1 plus C2 is equal to 0. Now I'm going to put equations 1 and 4 together to get 6 C1 plus 4 C2 is equal to 0. 6 C1 plus C2 is equal to 0. And subtract, I get 3 C2 is 0. So I know that C2 is 0. Well, C2 is 0, then we can go back here. I can get that C2 is a negative 6 C1, or that C1 is equal to a negative 1/6 of 0, so C1 is 0. Well, if I have that C1 is 0, C2 is 0, then notice here, I have a negative 7C1 plus 6C2 is equal to 2. Well, that can't be, because I can't have a negative 7 times C1, that would be negative 7 times 0, plus 6 times 0 can't be 2. So we reach a contradiction, which means it's impossible to solve that system of equations, which means that it's impossible to write 0, 2, negative 1, 0 as a linear combination. So determine whether the vector can be written as a linear combination? The answer is no. In trying to find C1 and C2, we get a contradiction. So we got a contradiction in trying to find C1 and C2. Again, the contradiction is using 1 and 2, I find that C1 and C2 must be 0. But C1 and C2 are both 0, then equation 2 can't be true. Neither can equation 3. So we've reached a contradiction. If every vector v in a given vector space capital V can be written as a linear combination of vectors u sub I in a set S, then S is a spanning set of V. So, if every vector in a set or in a vector space capital V can be written as a combination of other vectors that are contained in set S, then S is a spanning set of V. In this case, we say that S spans V. Show that S equal to 1, 0, 0, 1 spans R squared. Well, let's let V equal to xy be any vector in R squared. Well then, if S spans R squared, then I must show that the vectors in S can be written as, and that xy can be written as a linear combination of the vectors in S. So if that is true, then we would have that xy would equal to C1, 1, 0, plus C2, 0, 1, which would equal to C1, 0, plus 0, C2, which is equal to C1, C2. So whatever x, y you come up with, all I need to do is to say let x equal to C1 and y is equal to C2, and we have the vector. So you come up with vector xy, then I can come up with C1 and C2. So anytime you come up with a vector, it's easy for me to pick C1, C2. So therefore, 1, 0, 0, 1 spans R squared. It's always possible to find the constants so that the vector you come up with is a linear combination of 1, 0, 0, 1. One, 0, 0, 1 is a standard spanning set of R squared. Sometimes you'll see it written as the set IJ, vectors IJ, where I was defined to be the vector 1, 0, J was defined to be the vector 0, 1. So you might see I and J occasionally, especially in your physics classes. Show that 1, 3, negative 2, negative 6, 4, 12 does not span R squared. Well, again, let's start assuming that it does and see if we reach a contradiction. So we'll let V equal to the vector x, y, which would be in R squared. Well, if it does span it, then that means I can write x, y as a linear combination of these three vectors. So I can find C1, C2, and C3 such that C1 times 1, 3 plus C2 times a negative 2, negative 6 plus C3 times 4, 12. So xy would equal to xy is a linear combination of these three vectors. Well, this would be C1, 3C1 plus a negative 2, C2, negative 6, C2 plus 4, C3, 12, C3. Or it would equal to C1 minus 2, C2 plus 4, C3, 3, C1 minus 6, C2 plus 12, C3. Equating coefficients, I get that C1 minus 2, C2 plus 4, C3 is equal to x. I get 3, C1 minus 6, C2 plus 12, C3 is equal to y. Or I have the matrix 1, negative 2, 4 with the x, 3, negative 6, 12, y. Let's multiply row 1 by negative 3, add to row 2. One, negative 2, 4, x. Now I'm going to multiply row 1 by negative 3 and add to row 2. Negative 3 times 1 is negative 3 plus 3 is 0. Negative 3 times negative 2 is 6. 6 minus 6 is 0. Negative 3 times 4 is negative 12. Negative 12 plus 12 is 0. Negative 3 times x is negative 3x plus y. So thinking of equations, what this is telling me is 0 is equal to a negative 3x plus y. Well, this is not true for all x and y an element of real numbers. So I can find at least one that's not true for. Because let's let x equal to 1, y is equal to 1. Well, then I would get 0 is equal to negative 3 plus 1. 0 is equal to negative 2, which is not true. So we can see right off that the set does not span all of R squared. what part does it span? It spans the set of all ordered pairs x, y such that y is equal to 3x. X, an element of R, y, an element of the set of all real numbers. So it will span part of it, but not all of it. So it does not span all of R squared. If S is a set of vectors in a vector space V, so S is a set of vectors in a vector space V, then the span of S, denoted by this symbol, is a set of all linear combinations of the vectors in S. So the span of S is a set of all linear combinations of the vectors in S. Now we get a very important theorem. If S equals vectors V1, V2 out to Vk is a subset of a vector space V, then the span S is also a subspace of V. So if S is a subset of V, then the span of S is a subspace of V. Also, the span of S is the smallest subspace of V that contains S. The span of S is the smallest subspace of V that contains S. Now I need to define smallest for you. So smallest in the sense that every other subspace of V that contains S must contain span of S. So this is what I mean by the smallest that would do it. If I find any other subspace of V that contains S, then that subspace must also contain span of S. Let's look at the proof. Let's prove part 1 first. That span S is the subspace of V. Now remember, to prove that something is a subspace, I've got to prove 3 things. That it's not empty, vector addition is closed, scalar multiplication is closed. So that's what we have to do for span S in order to prove that it is a subspace. So as far as proofs is concerned, that's automatic. That's what you've got to do. So let's look at the proof of part 1. Let U and V be vectors in span of S. Now since U and V are in span of S, that means U and V are linear combinations of vectors. So U would be C1V1 plus C2V2 and so forth. V would be D1V1 plus D2V2 and so forth. So if U and V are in span of S, then that means U and V are linear combinations of vectors that are in set S. Whereas V1, V2 through Vk are vectors in set S. And of course for C's and D's are scalars. I've been using just the C's, but this case, since we've got U and V, I use C's for U and D's for V. They're just real numbers. Now, clearly span of S is not empty, because if S has a vector in it, then the span of S would have all the constants times that vector. So clearly it's not empty. Now let's look at U plus V. Well, to add U plus V, I just add the like terms, the like components. So U plus B would be C1 plus D1 V1 plus C2 plus D2 V2 out to CK plus, this should be D here, V sub K. Well, since so then that means U plus V is a linear combination of the vectors V1, V2, and Vk, because C1 plus D1 is just a scalar, C2 plus D2 is a scalar, Ck plus Dk is a scalar. So U plus V is a linear combination of vectors V1, V2, and Vk. Well, since the span S is the set of all possible linear combinations of vectors in S, then U plus V, which is a linear combination of vectors in S, must be in the span of S. So we have closure under vector addition. Now CU, if we go back and multiply C by vector U, would be C times C1 V1 plus C times C2 V2 and so forth. Well, C times C1 is just another scalar. C times C2 is just another scalar. So I see that CU is a linear combination of the vectors in S. So CU is in the span of S. So we have closure with respect to addition, closure with respect to scalar multiplication. So span S is the subspace of V. So that's a fairly straightforward proof. Part 2 is a little more subtle. Let U be any other subspace that contains S. What we must do is to show that span S is a subset of U. In other words, if U is any other subspace that contains S, then U must also contain span of S. In other words, every element of span S is an element of U. So everything in span S is also in U. Now this is the sense that we're trying to show that span S is the smallest set that will span the vectors. Let me get the theorem proof back that we're doing. Span S is the smallest subspace of V that contains S. That's what we're showing. So let's let U be an element of span of S. Now if U is in span of S, that means U is a linear combination of the vectors in S. C1, V1 plus C2, V2 and so forth. So all these vectors, V1, V2 and so forth, are in S. And U, a linear combination of those, would be in span S. So we're saying the VI is in S. That means that's just the same as saying V1, V2. So I could stand for 1, 2, so forth up to K. Now, VI is in U. Well, how do I know that VI is in U? Well, U contains S. The VI vectors are in S, so therefore they must be in U. We know U is a subspace, so since U is a subspace, the vector U is in the subspace of U. Now, how do I know that since U is a subspace, vector U is in U? Well, if U is a subspace, that means that it's closed with respect to vector addition and scalar multiplication. Well, we have here that VI, the V's, are in U. So if the V's are in U, then C1V1's in U, C2V2 is in U, CKVK is in U by closure of scalar multiplication. The sum would be in U by the closure of vector addition. Now if all the V's are in U and U is in U, we have proved that every element of the span of S is also an element in U. So we proved that the span S is the smallest subspace of V that contains the set S.